When a switch leg comes into contact with a grounding conductor, several issues can arise, leading to a humming noise in the electrical panel and a failure of the breaker to trip. This situation typically indicates a ground fault. The humming noise and lack of breaker tripping suggest a short circuit between the hot wire and the grounding conductor. Here's an explanation of what might be happening. Firstly, the grounding conductor creates a path for the fault current to return to the panel. However, if this path exhibits high impedance, such as due to loose connections or grounding rod problems, it can restrict the current flow. This limited current flow may not be sufficient to trigger the breaker to trip. Secondly, as the current traverses this high impedance path, it generates a magnetic field. This magnetic field, in turn, causes the panel to emit a humming sound. The humming sound serves as an indicator that current is flowing within the system, even though the breaker remains in the on position. Thirdly, the breaker itself might lack the necessary sensitivity to trip at the relatively low level of fault current that is present. This insensitivity could stem from the breaker's inherent design or from the effects of aging on its internal components. Several potential causes could contribute to this scenario. One possible cause is loose connections in the grounding circuit, including connections at the grounding rod or within the panel itself. Another cause could be a damaged grounding conductor, which increases the resistance of the ground path. Improper grounding practices, such as daisy-chaining grounding conductors, can also create a high-impedance ground path. An insufficiently rated breaker for the circuit can also fail to trip under the fault conditions. To address this issue, follow these steps. Safety is paramount, so always turn off the power to the circuit at the breaker before commencing any diagnostic or repair work. Use a voltage tester to pinpoint the location of the short circuit between the switch leg and the grounding conductor. Thoroughly inspect the grounding circuit, ensuring that all connections are secure and that the grounding rod is properly installed and in good working order. If you discover any damage to the grounding conductor, replace it with a new conductor that meets the appropriate specifications. Tighten all connections in the panel and at the lighting fixtures to eliminate any potential sources of high impedance. If the existing breaker seems insensitive or unreliable, consider replacing it with a more sensitive model that is specifically designed for ground fault protection. After completing the necessary repairs, turn the power back on and test the circuit to verify that it is functioning correctly and safely. When investigating a humming noise in an electrical panel coupled with a failure of the breaker to trip despite a ground fault, it is essential to systematically examine the grounding system and the breaker itself. The grounding system should have a lower impedance path back to the source. Any issues like corrosion, loose connections, or undersized conductors can raise the impedance and limit the fault current. This reduced fault current may not reach the level required to trip the breaker, leading to the humming noise as current leaks to ground. Inspect the grounding electrode conductor, which connects the grounding system to the grounding rod or other grounding electrode. Ensure it is intact, properly sized, and securely connected at both ends. Corrosion can develop at these connection points, increasing resistance. Check the ground rod clamp, the point where the grounding electrode conductor connects to the ground rod. This connection should be free of corrosion and tightly fastened. Verify that the ground rod is properly installed and driven deep enough into the earth to provide a good ground connection. The depth requirement varies depending on local codes and soil conditions. The grounding system within the panel itself is also critical. Ensure that all equipment grounding conductors, which are the wires that ground metal enclosures and equipment, are securely connected to the ground bus bar in the panel. Look for any signs of loose connections, corrosion, or damage to these conductors. Pay close attention to the neutral bus bar. While the neutral and ground are bonded at the service entrance, any loose connections or issues with the neutral can indirectly affect the grounding system's performance. Breakers are designed to trip when they detect an overcurrent or a ground fault. However, breakers can degrade over time or be improperly sized for the circuit. If the breaker is old or has been subjected to numerous trips, it may become less sensitive and fail to trip at the appropriate current level. Verify that the breaker is the correct size for the circuit it protects. An undersized breaker will trip too easily, while an oversized breaker may not trip when it should. Replace any breakers that are known to be faulty or are suspected of being unreliable. Consider using a ground fault circuit interrupter, or GFCI, breaker for circuits that serve areas where ground faults are more likely, such as bathrooms, kitchens, and outdoor locations. GFCI breakers are designed to trip at very low levels of ground fault current, typically around 5 mA, providing enhanced protection against electrical shock. A multimeter can be used to measure the voltage between the hot wire and ground, as well as the resistance of the grounding path. A high voltage reading between hot and ground indicates a ground fault, while a high resistance reading on the grounding path indicates a problem with the grounding system. An insulation resistance tester, also known as a megameter or megger, can be used to test the insulation of wires. This test applies a high voltage to the wire and measures the leakage current to detect insulation breakdown, which can cause ground faults. An earth ground tester can be used to measure the resistance of the grounding electrode. This test involves driving auxiliary ground rods into the earth and measuring the resistance between the main ground rod and the auxiliary rods. This test provides a more accurate assessment of the grounding system's effectiveness than a simple resistance measurement with a multimeter. Electrical codes such as the National Electrical Code, or NEC, provide detailed requirements for grounding and bonding. These requirements are designed to ensure that electrical systems are safe and effective. Consult the NEC for specific requirements related to grounding conductor sizing, grounding electrode installation, and bonding practices. Bonding refers to the practice of connecting all metal parts of an electrical system together to create a common ground potential. This helps to minimize the risk of electrical shock by ensuring that all metal parts are at the same voltage. Bonding can be achieved by using bonding jumpers, which are short lengths of wire that connect metal enclosures, conduit, and other metal parts. The size of the bonding jumper must be appropriate for the size of the circuit conductors. The NEC specifies the minimum size of bonding jumpers based on the size of the circuit conductors. Grounding and bonding are critical safety measures that help to protect people from electrical shock and prevent electrical fires. By following proper grounding and bonding practices, you can ensure that electrical systems are safe and reliable. Remember to always turn off the power to the circuit before working on any electrical components. Use properly insulated tools and wear appropriate personal protective equipment such as rubber gloves and safety glasses. If you are not comfortable working with electricity, consult a qualified electrician. The NEC Table 250.122 provides the minimum size of equipment grounding conductors for grounding raceway and equipment. For example, if the overcurrent protective device is rated at 20 amps, the minimum size of the copper equipment grounding conductor is 12 AWG. If the overcurrent protective device is rated at 60 amps, the minimum size of the copper equipment grounding conductor is 10 AWG. The NEC Table 250.66 provides the size of grounding electrode conductor for alternating current systems. For example, if the size of the service entrance conductors is 2 AWG or smaller copper, the minimum size of the grounding electrode conductor is 8 AWG copper. If the size of the service entrance conductors is 3/0 AWG or larger copper, the minimum size of the grounding electrode conductor is 2 AWG copper. The NEC Section 250.50 requires that all grounding electrodes that are present at each building or structure served shall be bonded together to form the grounding electrode system. This includes metal underground water pipes, metal frames of buildings, concrete encased electrodes, and ground rings. The NEC Section 250.52 specifies the types of grounding electrodes that are permitted. These include metal underground water pipes, metal frames of buildings, concrete encased electrodes, ground rings, and rod and pipe electrodes. Rod and pipe electrodes must be at least 8 feet in length and must be driven into the earth to a depth of at least 8 feet. The NEC Section 310.16 provides the ampacity of conductors. The ampacity of a conductor is the maximum current that it can carry continuously under specific conditions of use without exceeding its temperature rating. The ampacity of a conductor depends on its size, insulation type, and the ambient temperature. For example, a 12 AWG copper conductor with THHN insulation has an ampacity of 30 amps when installed in a raceway or cable. 10 AWG copper conductor with THHN insulation has an ampacity of 35 amps when installed in a raceway or cable. The NEC Article 100 defines various terms related to electrical wiring and equipment. Some important definitions include ampacity, which is the current carrying capacity of a conductor, bonding, which is the permanent joining of metallic parts to form an electrically conductive path, grounding, which is the connection of a conductive body to the earth, and overcurrent, which is any current in excess of the rated current of equipment or the ampacity of a conductor. In practical terms, if you encounter a humming noise, begin by de-energizing the circuit. Then, visually inspect all accessible wiring and connections for any signs of damage, loose connections, or corrosion. Pay particular attention to the grounding connections at outlets, switches, and light fixtures. Use a multimeter to verify the voltage between the hot wire and ground. A reading of 120 volts indicates a direct short to ground. Next, measure the resistance of the grounding path. A low resistance reading, ideally close to 0 ohms, indicates a good ground connection. A high resistance reading indicates a problem with the grounding system. If you suspect a problem with the breaker, test it using a breaker tester. This device applies a simulated overload to the breaker and measures the time it takes to trip. If the breaker fails to trip within the specified time, it should be replaced. Remember, working with electricity can be dangerous. If you are not comfortable performing these tests and repairs yourself, consult a qualified electrician. Always follow proper safety procedures and wear appropriate personal protective equipment. If the humming persists after checking all connections and components, there might be other factors at play, such as harmonic distortion or electromagnetic interference. These issues can be more complex to diagnose and may require specialized equipment and expertise. In such cases, consulting with an electrical engineer or a qualified electrician with experience in power quality analysis is recommended. It is also important to consider the age and condition of the electrical panel itself. Over time, electrical panels can deteriorate due to corrosion, loose connections, and other factors. If the panel is old or shows signs of damage, it may be necessary to replace it. Replacing an electrical panel is a major undertaking that should only be performed by a qualified electrician. Regular maintenance and inspection of electrical systems are essential for ensuring safety and reliability. Schedule periodic inspections by a qualified electrician to identify and address potential problems before they become serious hazards. This includes checking for loose connections, corroded wiring, and damaged components. Also, ensure that all electrical work is performed in accordance with the NEC and local codes. This helps to ensure that the electrical system is installed and maintained safely and correctly. Furthermore, consider the impact of any recent electrical work or modifications on the grounding system. If any changes have been made, ensure that the grounding system has been properly re-established and that all connections are secure. Sometimes, seemingly unrelated electrical issues can affect the grounding system. For example, a faulty appliance or piece of equipment can introduce noise or distortion into the electrical system, which can then manifest as a humming noise in the panel. Try disconnecting any recently added appliances or equipment to see if the humming disappears. If it does, then the appliance or equipment may be the source of the problem. When working on electrical systems, it is important to have a good understanding of electrical theory and the principles of grounding and bonding. This knowledge will help you to diagnose and troubleshoot electrical problems more effectively and safely. There are many resources available to learn more about electrical theory, including textbooks, online courses, and training programs. Investing in your electrical knowledge can help you to become a more confident and competent electrical worker. Always remember that safety is the top priority when working with electricity. Take your time, follow proper procedures, and never take shortcuts. If you are unsure about anything, consult a qualified electrician. Electricity is a powerful force, and it should be treated with respect. By following these guidelines, you can help to ensure that electrical systems are safe and reliable for everyone.